listen to the silence of space. Tonight, we will fall asleep to stories about the space station and those who work there. Just close your eyes and let the voices from NASA take you to the stars.
Houston, we have a podcast. Welcome to the official podcast of the NASA Johnson Space Center. I'm Gary Jordan, and I'll be your host today. So before we cross into the new year and witness the spectacle of thousands of fireworks launching everywhere, for episode 25, we're talking about rockets, specifically a special rocket that's, well, on a rocket. So today we're talking about launch abort systems with Wahab Al-Shaheen. He's a guidance, navigation, and control engineer here at the NASA Johnson Space Center in Houston, Texas. And we had a great discussion about what a launch abort system is, how it works, a little bit of history, and why they're necessary to send humans into space. So with no further delay, let's go light speed and jump right ahead to our talk with Mr. Wahab Al-Shaheen. Enjoy.
T-minus 5 seconds and counting. Mark. All launch commit lights are correct. There she goes.
Houston, we have a podcast.
But Wahab, it's really good to see you, and thanks for coming on the podcast today, for taking the time to do this.
Of course.
This is an interesting topic because it's sort of, we've been talking a lot about a lot of big things, right? We talking the International Space Station. We talked about space food, landing for these big concepts. But this is sort of it is a big concept, but it's kind of like, if you're looking at a rocket, you're looking at the tippy top of a rocket.
Yeah.
So that's kind of what this is, right? This is about I titled this "A Rocket on a Rocket." Is that a fair way to say it?
So when you told me that you mentioned you were trying to call it a rocket on a rocket, I thought about that, and then I thought about the specifications for what this thing actually does.
Yeah.
It's 30 feet tall. It produces 400,000 pounds plus of thrust.
Whoa.
That is basically, you at that point, yes, that is a rocket that is sitting on top of an even larger rocket. So certainly that's a fair assessment.
Oh, wow. All right. Yeah, I didn't think, guys, I was like, it kind of is, right? Because the whole point of this is, it's called a launch abort system, correct? So
that's right.
If a rocket is launching and something goes wrong, there is another rocket on top of it that can safely get our crew members away.
That's correct.
Is that kind of the overall concept of why this is what it is?
Yeah.
Okay.
So with regards to the capability, it is the primary purpose is to separate the crew module from the launch vehicle that may or may not be having a problem. So whether or not you use a tower or you have built-in engines, like some of our private partners like SpaceX and Boeing have built-in engines as opposed to a tower, that's up to the design engineers, but first and foremost, it's separating the crew from the failing launch vehicle. That's the primary purpose.
Awesome. So that's kind of the overarching, what is the purpose of this?
That's right.
That's pretty much it. Okay. So like you said, what was that number you said at the very beginning? How many pounds of thrust?
So for the Orion launch abort system, the abort motor that separates that crew module from the launch vehicle generates about 400,000 pounds of thrust.
Whoa.
Yeah.
Okay.
Yeah. So it
so
is
a lot.
Yes. Yeah.
Wow. What compared to, when you think about it, you're talking about, it's called aborting a launch, right? So really you're escaping from a speeding rocket.
That's right.
Right? So what kinds of, that's the energy that really has to go into that. So how does that happen?
Yeah. So again, I work on the Orion launch abort system. So I'm speaking from what we're doing on that project. But like I said, there are different kinds of launch abort systems and people do things differently. But in general, you have to be able to provide capability to separate from the rocket all the way from when it's on the pad, essentially prior to launching, up to prior to going into orbit. So that design space is 0 feet in altitude to 300,000 feet in altitude and traveling at 0 miles per hour to 7 times the speed of sound.
Whoa. So
a single system has to be capable and robust enough to provide abort capability throughout that entire spectrum.
Okay.
So you can imagine, you have to have enough thrust capability to separate when you're not moving, but also when the vehicle is traveling at thousands of miles per hour.
Whoa. Okay.
Yeah.
But there's so you said, you kind of hinted at this. There's different types, right? And so for you specifically, you're working on Orion.
That's right.
And I can't believe it, but up until this point, we actually haven't had a podcast that's just the overall concept of Orion. We're actually starting with the launch abort. So let's go back and let's talk about, what is Orion?
Sure.
What are you designing this launch abort system for?
All right, so in general, Orion is the crew module that's going to be built to house our astronauts and take them to low Earth orbit, as well as our deep space missions. So whether that be to the moon or Mars.
Okay.
So that's just the capsule itself.
I see.
The part that I work on is the tower that is attached at the top of the crew module, which is on top of the large space launch system, which is our rocket. In total, the rocket plus the crew module plus the abort system is about 330 feet high.
Woo!
Yeah.
Okay.
So it's a big rocket. Yeah.
Yeah, it's like a tall building.
That is basically a tall building.
Yeah,
that's right.
that's amazing. Okay, cool. So if I'm imagining, the Orion capsule, right? If I were to imagine a shape, I'd kind of imagine it mostly like a capsule or like a sort of the rounded trapezoid. Is that a fair?
A rounded trapezoid is definitely fair. Yep, that's right.
So if you're imagining a rounded trapezoid with the angles inward going, or the angles on the side going up, you kind of just fit this, you said tower right on top of it?
That's right, yeah. And the Orion design actually calls for a shroud that actually encompasses and goes around the Orion crew module itself. So we have a shroud that covers the capsule itself.
Okay, so it's not just a tower, a pole sticking up. You're actually covering the.
Yeah. Previously for Apollo and Mercury, it was just the tower. I see. But we opted for a shroud instead for better aerodynamics.
I was just about to ask
one
why.
reason.
Okay,
among
very
others.
cool. All right. Well, so the idea is that, like you said, the purpose is to safely get the crew away from a speeding rocket, or in several different scenarios, right? So what needs to happen, right? Just in general, talking about the general concept of the launch abort system, it's not just fire a rocket and just go wherever you need to go, right? There's some intricate engineering that goes into that.
That's right. I call it an abort ballet. Yeah, it is. It's definitely. This is probably one of the hardest things to work on in engineering. Like I said, just because you have to design something that's so robust, that's built to work in any contingency failure. So it's kind of like Murphy's Law. You have to assume what can go wrong will go wrong.
You have to be the devil's advocate in every situation. Yeah.
Exactly. So for Orion specifically, there's 3 motors. So let's just visualize this in your head. You're going up on the rocket and you're at some altitude, barreling towards space. The mission's fine. Okay. Something happens and there is either a software switch or some kind of signal that indicates that there's something wrong with the launch vehicle. That gets sent to the flight computer. The flight computer says, all right, we need to escape. As soon as that command is sent, the abort motor is ignited and it starts burning, and that burns for about 5 seconds, and that does the heavy lifting of separating the crew module from the launch vehicle.
Is it fair to say that's the most powerful?
That's right. It definitely is. Yeah.
Okay.
The abort motor is it's completely passive. It's not controlled in any way. It just fire and go. It just separates the crew module from the launch vehicle.
So there's no big red abort button in this scenario,
there is
right?
not.
It's
no,
automatic.
This is
detects
all
a
automatic.
problem okay.
That's right. So once we've separated, there's another motor that's on top of it kind of acts like a very large lever arm at the top of the 30-foot abort tower, and that's the attitude control motor. It's the most complex motor of the 3 that are inside in the launch abort system, and the purpose of that one is to literally flip. You're basically doing a front flip in midair of the crew module, because if you imagine we just separated, we're facing with the tower pointed forward. In order to deploy the parachutes, we have to go heat shield forward. So we have to do an entire 180-degree reorientation maneuver so that the capsule is falling blunt end first.
Whoa. Okay, so you fire the super powerful rockets to get away from the larger rockets that you're on top of, and then you fire more rockets so that you do a front flip and get oriented. Okay, so it's very complex.
Yep. And then once you are in the orientation that you want for deploying the parachutes, there's a third motor, the jettison motor, that actually separate. Now there's another separation of the launch abort system, which you no longer need
because it already did the front flip.
That's right. Yeah. From the crew module.
Okay.
Yeah.
Cool.
So there's 3 separate motors on the launch abort system that have nothing to do with getting you to space. Yeah.
It's just to get you away from this rocket
that
doesn't, I guess, is not going to take you to space anymore.
Yeah.
So the launch abort system is just a series of motors, a series of rockets, right? The parachutes are completely separate.
That's right.
Once it does that separation, then the parachutes are coming from the capsule itself.
Exactly. Okay. And depending on how high we are in altitude, the parachute sequence is no different than what it would be if we were coming back from a mission. Say we had a successful mission, we were deploying the parachutes, it goes through that same process essentially.
I see.
Yep.
Okay, so there has to be a story behind how you got to this. Did you say rocket ballet? Is that what you call it?
Yeah. Or abort ballet.
Abort ballet. Yeah, there has to be a story to it. So how did launch abort systems come about? What was the initial, design of the system?
So obviously it was first conceived when we were thinking about human spaceflight. So back in the 1950s and 60s during the Apollo mission.
Okay.
So that was first and foremost. We knew that this was a dangerous field, especially back then, doing it for the first time. We didn't necessarily expect failures, but we knew that those were a high, they were high in likelihood.
Yeah.
So we had to design something to save the crew in the event of one of those emergencies. So that's kind of where it all started, and ever since then, we've every human-rated vehicle that goes to space has to have a escape mechanism, and that just varies across different people who are designing it.
Nice. Okay, so how did they, what were some of the early designs, and kind of how did you go from those early designs to more modern? Like, what did you learn along the way?
Yeah, so all of the early designs, and by early designs I'm talking about the early Soyuz, Mercury, Apollo, all of those were a tower design.
Okay.
So however that was conceived, that people decided that was the way to do it. It made the most engineering sense, just something to pull the capsule away from the launch vehicle that's failing. So all of those kind of operated the same way, and for all of those systems, they're all passively controlled, so they're not actively controlled. So the motors are not controlled in any way. They just burn and separate the crew, and then dispose of the crew capsule so that it can separate deploy the parachutes.
Okay.
Yeah, so all of those are passively controlled. We've kind of moved into the world of active control. So that's where we are now. Like I said, the Orion launch abort system, is completely the attitude control motor portion of it that actually steers the abort motor.
The front flip.
Yep, the front flip is controlled. Yeah, you would not be able to do that with a passive system.
Okay.
So yeah, that's actively controlled.
For different rockets, there had to be different designs, right? So the tower design seems to be a pretty good one for a upward-facing rocket. I know something had to change for the shuttle era, right?
That's right.
Okay.
Yeah, so the shuttle era was a little interesting because it was basically a space plane essentially that was attached to the side of an external tank and 2 solid rocket boosters. And unfortunately, I don't think we had we definitely don't have as great of a abort capability on the space shuttle as we do on Orion. Kind of one of the main reasons we've shifted back towards the long monolithic rocket with the capsule on top.
Sure.
It's just a safer design in general.
Yeah.
And most people don't know this, but for the space shuttle, you could not do an abort from the space shuttle stack until the solid rocket boosters were completely burned out.
Oh, so even you had to keep ascending.
That's
no matter,
right.
Wow.
There was no abort capability until solid rocket boosters burned out, which was about 2.5 minutes.
Oh, wow.
So 2.5 minutes, that puts you at about 140,000 feet.
Wow.
That's basically halfway up to the current abort capability. I mean,
Yeah.
I mentioned earlier. The Orion launch abort system is capable up to 300,000 feet, so half of that is about 150.
Right.
So for half of that entire region, you couldn't abort. But now with this system, post space shuttle, we can. We have that abort capability.
And your window's that much smaller, right? Because you're constantly accelerating up there, so even the window from 150,000 feet to 300,000 feet that's a quicker window.
Exactly.
Wow.
Yeah. So again, that's kind of a side topic, but one of the reasons we went back to the stack monolithic approach.
Got it. Sure.
But for our design, like I mentioned this earlier, if we don't have an abort, that entire abort tower and all those motors are just jettisoned. We don't use them at all. So they serve no purpose outside of an abort.
I see. When are they jettisoned? If for an Orion mission, right? Say the Orion, the SLS is on top of, is the rocket, right? Space Launch System. That's the one that we're designing, and you put the Orion right on top. Everything goes according to plan. You're in space. You're doing your thing. At what point is the launch abort systems gonna say, I'm not needed anymore. I'm gonna detach?
Yeah, like it's a little after 300,000 feet, and at that point you could still have an abort. We just wouldn't use the launch abort tower. We would use the service module.
Oh, okay.
Yeah,
so that's the part that, if you're looking at the rocket, is underneath.
That's right. Yep.
I see.
And so we would use that engine for an abort to orbit or something like that.
Okay.
Yeah.
Okay.
So at that point, your requirements aren't necessarily come back to the Earth. You are high enough that you can abort to orbit, some low Earth orbit, and then or not lower, but some lower orbit and then come back.
Yeah, it's not like, I need to get back right now.
That's
Let's
right.
launch in. Okay. So you got some time, and you have to. It's different physics, right? Now you're in orbit. Now
There's no air drag or very little rather.
Yeah, so you're talking about a whole nother thing. We'll have to do another podcast.
That's right.
Okay, very cool. So, going back to Orion, we talked a little bit about, the history of launch aborts. It seems like it was just tower, and let's just keep improving it. So, we'll get into the weeds a little bit. What are some of the cool things? You mentioned a shroud. Shroud is one of the things that's different about Orion, but what's some of the other parts that are different?
From the heritage technology the heritage designs that we had in the past, we being NASA, the biggest thing is actively controlling this.
It's the front flip.
So
it is. Keep going back to that.
Yeah, it's you can call it front flip. That's fine. The entire system has its own flight computer and flight brain. So it's one extra level of complexity. And like I said, being an engineer on the project, it's really interesting to kind of work on it day in, day out. But you have to over-design everything because you don't know how this thing is going to be used. So in the event that we have to use this, it implies that the launch vehicle had exploded, had failed, had broke up.
Right.
Something was happening that triggered an abort. So you have no idea whether or not you're facing down, facing up, falling forward. It's just, you could be at any condition.
Yeah, you're talking about, I can't even think of a number. You're talking about a lot of different scenarios.
That's right.
And it has to work in all of them.
That's right.
Interesting. Okay.
Yeah.
So I think you may have addressed this before, but I'm going to come back to it. But, there's a reason that the Orion does this move, has the active motor, has the ability to do a front flip. Why did some of the older rockets not need that? Why were they only passive?
So some of those engines, they didn't necessarily require the pitch over portion of the abort, so they would actually separate, and it was kind of pointed in a direction. The engines were pointed in a direction to separate you out and away.
So no matter what, it was going away.
It was going away, right, yeah. So this is a little more intricate, and we have more requirements.
I see.
Yeah.
Does it have anything to do with the fact that we are talking about escaping from a much larger, much bigger rocket?
No, not necessarily.
Very cool.
Yeah.
So, what are some of the challenges of designing an active system? You said there's a lot of computer work that goes into it, but what are some of the things that you've encountered?
The portion that I told you about, designing for Murphy's Law. We end up using a lot of time to run simulations for all of these contingency scenarios that we would otherwise, it's hard to say what will go wrong, so we just design for everything.
Yeah.
So it's quite complex to make sure that, I have this great idea for design, you put it in, it's like, okay, that's great, but it only works in this small region. It has to work for...
a bunch of different scenarios that can happen up
right.
to 300,000 feet, right? So you got to think of everything within that space.
Yeah. And to take it away from technical, you'd appreciate this.
Yeah.
Another challenge of working on a launch abort system. So I've been at NASA full time for over 6 years now.
Okay.
And this is kind of my main project, and I've done some other work on some other vehicles, but the Orion launch abort system has been my main project. So for 6 years of my full-time experience here at NASA, I've worked on something. It's weird to say, but I'm working on something that I hope never flies. Because if we ever had to use this thing, it implies that, like I said, the launch vehicle, we lost the mission, and you're putting the crew's life in jeopardy. It's nothing you want to, even if it succeeded, the mission's failed, and now we have to figure out what happened on the launch vehicle. So it's never going to be a good day when we have to ever use it. So any mission that we have in the future, I'm going to be happy that we didn't fly it.
But I mean, what you're saying makes sense, because you just said there's so many different scenarios that could happen.
Yeah.
So what's the thing that you have control over? Let's just over-engineer it. Let's design for everything, and that's your responsibility, and it's a big one, right? Because you hope it never flies, and that's a good way of saying it. Absolutely, because that means we're doing everything perfectly. Thumbs up, A-okay. But if it does, then you know this thing is going to work.
That's right, which is why I'm really excited for not actually flying this with humans on board, but pre-planned flight tests where we actually do perform an abort to test all that capability without humans on board.
Oh, okay.
Yeah, so we actually, before I started, we actually did that in 2010. We did a pad abort. So a pad abort is where it's just replicating it sitting on the pad, and then performing an abort while not on top of a launch vehicle.
I see.
Yeah.
Okay, so you just set, in this scenario, you just set the launch abort system
On the ground, essentially.
ground.
That's right.
and just tested to see if it would work at 0. You know, like
Yeah.
if the rocket was just there sitting, hasn't launched yet, and so how'd that go? How'd that test?
Fantastic test.
Right.
From all the people I've talked to that were there, and looking at all the design data after the fact, videos. There's tons of great videos on the NASA website and YouTube.
Yeah.
Perfect test. Everything went well, and the design's kind of matured a little bit since then, but we kind of still do the same thing where it's a great video. You can see that front flip I was talking about, to kind of get a better understanding of what I'm talking about in terms of what's going on.
So was it going back to is it just the launch abort system, or was there an Orion capsule mock-up?
Yeah, there was a boilerplate Orion capsule under there.
Nice.
Didn't necessarily have the avionics or anything on there,
Okay.
or any of the peripherals like the crew life support system.
Yeah.
But it was a boilerplate capsule that basically weighed about the same as the crew module would when you put humans on board.
Makes sense, right? You want to test that section.
yeah.
You want
I mean,
to pull that weight at a certain speed.
Yeah, you absolutely. And the crew module weighs about like 300 or 30,000 pounds. So you want to make sure that that weight is there.
Yeah, absolutely.
Yeah,
that's something you don't want to just say, we'll just assume. Yeah.
Right.
Awesome. I have seen that video before, and it is super cool, especially the I don't know if it's called super slow motion, but they do have one where it fires and you see those engines firing, and then the screen for a whole second just goes it goes black a little bit, right? So you just see it's so bright that the camera is adjusting its exposure. It's like, whoa, and it goes bright black for just a second and then shoots straight up. It's super cool.
I know exactly what part you're talking about.
Yeah.
And next time you're watching that slow motion video, and while they're going through the pitch over maneuver, the reorientation maneuver where they're actually doing that flip,
Yeah.
put like ballet or classical music in your head. And that's kind of why I feel like that.
The abort ballet.
Yeah, it's just this thing flying through the air. And
Dun, dun,
Yeah.
dun, dun.
Yeah.
All right.
And that's kind of why every time I see that video, that's what I think in my head. But that's just me.
Very cool. Awesome. Yeah, I'm definitely gonna we'll see. Do you know where on the website it is, where we can actually point some folks to go listen to it? And what's the test called? Maybe
Sure,
I can just search
that's the easiest way. NASA videos that are on YouTube is the easiest way. It's Pad Abort 1.
Pad Abort 1.
Yep.
Okay, everyone.
And it was in
that's where you
2010.
Okay, Pad Abort 1 back in 2010.
That's right.
Awesome. So what have you done since 2010? That you said there's been some changes.
There's been some minor changes to both the hardware and the software.
I see.
But ever since I've started, we're gearing up for the next portion of the testing phase, which is actually putting the some boilerplate Orion capsule, the launch abort system, on a booster, not necessarily the entire rocket, but some booster, begin an ascent on the booster and then perform an abort from that flight condition. So doing an abort as opposed to from the pad while the vehicle is moving.
A rocket on a rocket.
A rocket on a rocket, that's right.
Cool. When's that one scheduled for?
April 2019 is the current time frame.
Okay.
Yeah.
All right. Do you know what kind of rocket you're going to be using?
Yeah, it's just a booster that's being designed by Orbital ATK.
I see.
Yeah.
Okay.
It's
cool.
an abort test booster, just a custom rocket.
Custom rocket just for this. They're very cool.
Yeah, nothing that's going to take you to space.
Yeah. But just because you have to test to actually escape from a speeding rocket, I can understand that. That's pretty cool.
So that's for me. That is the exciting flight test where I want to see this actually get used and work, and that'll be cool.
Yeah, that would be amazing. That's awesome. So there's another one too, right? Is there where we're talking about this in 2019? Is the launch abort system going to be part of EM1 or EM2 or anything like that?
Anytime there is crew on board, it will absolutely be on there.
Crew on board.
Yes.
Okay.
Yeah. So for EM1 is currently, or as of recently, not a crewed mission.
Okay.
So the launch abort system will not be used on that because we have no purpose for using it.
I see.
But for EM2, when the crew is on there, absolutely. Yeah. We will not be flying a crew without an abort mechanism.
Very cool.
Just because spaceflight is hard and you can't design for everything. You have to make sure that we have the crew safety is top priority in spaceflight.
So EM1, we keep referring to that. I try to stay away from acronyms on this show, but we'll go back to it. Is Exploration Mission 1, right? That's where we're actually going to put Orion on top of the Space Launch System
right.
and test out to make sure everything's okay. And that one actually goes to the moon, right?
That's right. Yeah, it does. It's going to circle around the moon and come back. So
yeah. It's going to go really far past the moon too when it circles around.
That's right.
It's going to be some good imagery.
Yeah. So it'll be an exciting time for the first time we have some human-rated vehicle going out towards the moon and coming back.
Yeah. First time in a long time. That's going to be awesome. Yeah.
Very awesome. Yes, I agree.
And EM2 is going to be later, but we're actually going to put a crew aboard, and they're going to do sort of the same thing, right?
That's right.
They're going to go around the moon, and that'll be a great mission to do. So. Just Orion in general, obviously, when we talk about this, the reason that I'm excited about this episode, just besides learning about this really cool technology, a rocket on a rocket, it just sounds so cool. But the idea that each part of the rocket has so much intricate detail that needs to be paid attention to.
Yeah.
You're talking about the launch abort system, Orion service module, all these different parts have to come together just right to make the whole thing. So, what are some of the challenges for Orion, for the capsule, but also the whole system, the whole idea of space launch system and going farther and deeper into space than ever before?
Yeah, you kind of, as you were listing all those things, in my head, I'm thinking about who are our partners through in the design process for building some of this hardware, and that's probably the most challenging thing. Like the service modules being built by the European Space Agency, the crew modules being built here, but Lockheed is the primary contractor. The abort motor engines are being built by Orbital ATK. So there's all of these people that are spread out all across the globe, really. That are helping to build portions of the Space Launch System. And even if they are here in the United States, they're spread across the United States. So that's one of the biggest challenges, and I deal with this every single day, is dealing with and working with people remotely, and trying to break those barriers to having efficient dialogue on a day-to-day basis. So
because you're all designing stuff for this one idea, right? For a rocket that's going to go into deep space, so you got to make sure you're talking and got to make sure everyone is on board for what's happening.
Absolutely, yeah.
It makes a lot of sense. Awesome. Wow, this was such a cool topic. Is there anything else about launch abort system that I may be missing, or something that we can go dive deeper into?
We could. So I think we touched upon some of the interesting aspects of it technically. Okay. I guess I can leave you with one little story about so it's historical testing. Okay. Just because I find this one fascinating.
Oh yeah.
So for the we're doing our ascent abort test, like I said, in 2019.
Right.
We also did ascent abort tests for the Apollo era missions. So this test is going to be very similar to that. So we designed some custom booster in the 1960s to test the launch abort system.
Okay.
So when we were actually going out there for that test, it was, I think, 1966. The booster fired. So now you're ascending through the atmosphere, and at some flight condition, the launch abort motor was going to be triggered to test the entire hardware. What actually happened was that something happened with the test booster during the design portion or the manufacturing portion, and the rate gyros were instrumented incorrectly, upside down or something.
Oh.
So the booster, as soon as it launched, started spinning. And it started spinning faster and faster and faster.
Whoa.
So instead of triggering an abort at some designated altitude, we actually had a real abort on an abort test because the launch vehicle actually ended up breaking apart.
How about that?
Yeah, so that is the best test that you can actually have for this flight system.
So it worked, right?
It absolutely worked, yeah.
Because it did its job.
That's right.
The rocket did something crazy.
Exactly.
And it did its job. That's fantastic.
Yes, that's like another example of that was not the intent of that test. The intent was not to actually replicate a launch vehicle failure, but that's what we got, and the system performed admirably.
Wow, I love that story.
It's just, I hope that doesn't happen for ascent abort test 2, but the one that we have.
Hey, well, if you're over-engineering it to do with any situation, you should be good to go. Yeah. I think you'll be fine.
And that one actually is there's a great video of that as well on YouTube. That's the Little Joe booster Apollo abort test.
Little Joe. All right, I'm going to mention that again once we Little Joe booster Apollo. Yeah. That's amazing. So cool. All right, Wahab, this was so cool. Thank you so much for coming on the show. For our listeners, if you want to stay tuned to after the music, we're going to tell you. We'll reference some of the videos that Wahab shared with us today, so you can go watch them. But a little bit more on how you can ask questions and be a part of this conversation. So Wahab, thanks again for coming on the show. It's been an absolute pleasure.
My pleasure as well.
Houston, go ahead.
Stop of the space shuttle.
Roger, 0G, and I feel
The
fine.
shuttle has cleared the tower.
Became a thief for all mankind.
It's actually a huge honor to break a record like this.
Not because they are easy, but because they are hard.
Never Houston, welcome to space.
Hey, thanks for sticking around. So today we talked with Wahab Al-Shaheen about launch abort systems, literally rockets on top of rockets. Super cool. If you want to know the latest updates of what's going on in that world, Wahab actually works on the Orion program. So if you go to nasa.gov/Orion, you can see all the latest updates there. They're also very active on social media, and we like to cover it on several accounts. You can go to the NASA Johnson Space Center account or the Orion accounts on Facebook, Twitter, and Instagram. Don't worry, they're all verified, so they're very easy to find. Just use the hashtag AskNASA or hashtag HWAP, HWHAP, on your favorite platform and submit an idea, or maybe you have a question about launch abort systems or Orion, and we'll make sure to address it on one of the later podcasts here. This podcast was recorded on July 12, 2017. Thanks to Alex Perryman and John Stoll. And thanks again to Mr. Wahab Al-Shaheen for coming on the show. We'll be back next week.